All right, welcome. So today it's our 10th week. We're almost done. So hope you guys have a project and are working on your models. So have a data set, train a model. You want to get it started soon since deep learning takes a while, unless you're doing like transfer learning or something. So good luck with that. So today's deep reinforcement learning. So what this basically is learning from trial and error. So basically you can think of just a person or a baby that has no knowledge of the world, and they interact with the environment and then they learn stuff. So what is that more exactly? So like I said, reinforcement learning is like learning with trial and error. Like we use like a reward punishment feedback system to train this agent. And so agent is basically the thing acting in this environment. So the agent would be Mario, and Mario can get coins and get reward, or his progression through the level is the reward. His punishment would be hitting an enemy and dying, for example. And so to the right, you can see how much reward Mario gets over time, and we would have to pre-specify that. Alright, so, and he tries to maximize the reward, so, and that is equivalent to our goal, which I'll explain again. So other examples of reinforcement learning, self-driving cars, you could form it as a reinforcement learning problem. Not necessarily they use that in industry, but they do use it to some extent. So your environment is like you're driving in a world or in a simulation, and you can detect like the variables of like what cars are surrounding you, what are the pixels of the camera, all these different inputs. And then what you try to do is produce some action in that environment. So that would be the steering angle or something. And similarly with like Pong on the right, you can pretty much put any game into this formulation, because the game would be the environment and your player would be the agent. So now let's go to definitions. So the first is reward. So a reward is a scalar feedback signal. It's just a numerical value. This indicates how well an agent is doing at some time step. And the agent's job is to maximize a cumulative reward. This also is called a goal. So by maximizing this reward, can we say always that it's the case that we get to some certain goal? And that's called the reward hypothesis. All goals can be described by the maximization of expected cumulative reward. So what does that mean? Well, if our goal is to get to some state, go some destination, for example, in a car, if we say that reward equals to 1, if we take the car and we get to the location, get a reward of 1, that means that we accomplished our goal. So that's a maximization of reward, because you got the highest possible reward, and then you got to the goal state. So next, we defined our goal, and now we're going to form our sequential decision making. So in making decisions over time, we have multiple dynamics. So our actions could have long-term consequences. For example, you write something down on a piece of paper, you throw it in the trash can, then someone picks it up and read it, and like from that deduces that you were at that location, and then like tries and tracks you down, I don't know, and something happens to you. Like this, words, actions could have long-term consequences. They can have immediate consequences, like you just throw it a bottle and it explodes, I don't know. like this is a very general framework, so yeah. And then rewards may be delayed, of course, and because like, for example, let's say you are, yeah, so like my example previously, like you might write something down and then someone might pick it up later and then give it to you in the future or something. Or a robot might do not something random, seemingly random, but in the end it took like one incremental step toward its goal. And then it might be better to sacrifice immediate reward to gain more long-term reward. So it might not be beneficial to simulate what would happen 100 steps down the line and simulate and actually take actions now, because, for example, we might eat a donut that's right in front of you instead of waiting more until we get 100 more donuts because someone gives you something. That's like a common thought experiment. How long does someone wait? If they give a donut every 10 minutes until a child just gives up and starts eating the donuts. So, and what we call the sum of rewards is a return, and it's basically the sum of the reward at each state, and then we just sum it up. So this is what the equation is for it. We have this thing called a discount factor. This is gamma, and this is what we weight our rewards, so that if we have something that's very low, then we always value the more near-term rewards. But if we have a very high reward, or if we have something that's 1, for example, then we equally weight all the rewards in the future. So everybody got this? All right, so next we have the agent environment loop. So an agent at the top, the brain, for example, we could take in our sensory inputs. We look around the world, we see something, that's our observation. That's very common sense knowledge. And then we would get a reward. Once we perceive the world, we can say, how good is this state to be in? So like, if I'm in the middle of an exam, that's probably pretty low. If I see a cake right in front of me, that's pretty high. And then we take an action based on what we see. And that is fed to an environment, and the environment decides what to do with that action. So this is basically our physics all around us. If I move my hand in a certain direction, it will, based on the laws of physics, move somewhere else. And that produces an observation and another reward for t+1. All right, good so far? All right. So now we move on to history and state. So history is just the definition of the word. It records everything that happened. And what happens is the observations, rewards, and actions. And then our state is a function of history. So a state encodes everything that's needed, anything that's useful to determine what would happen next. And surprisingly, or unsurprisingly, we have a state in our own minds. Like we unconsciously see around the world, and we produce some kind of state in our own minds, like what are the values of my hand positions? And we use that to produce different actions. So, like I said before, it interprets data. So the agent state is used for the agent to predict something. The environment state instead is all the information about the environment. So if you think about the universe, it's like every single atom or something. Or you could go further deeper or whatever. But it's all the information maybe in a simulation to produce what happens next. All right. So an information state basically is anything that you can use to predict what happens next. And so we want it to be equal to the agent state so that we can learn efficiently. So if the agent knows everything around it and what happens, then it knows what action will be the best by definition. And so we call this also a Markov state. And this is just some math of what it means. But basically, we want the future to be independent of the past. So that means that we don't have to go back and look over our history and then reevaluate what we know just to find out what the state is. We already are given the state, and so that has all the information necessary. Okay? So now we're moving on to fully and partially observable environments. So a fully observable environment basically means, say you're looking at a board game and you know where every single piece is on the board game. So that means you have full information. A partially information environment, or partially observable, means like you're in the real world, for example. You can only see what's in this room, and you don't necessarily know what's happening outside. So we call this MDP for fully observable environments and partially observable Markov decision process on partially observable environments. And what this implies for partially observable environments is you can never really infer what is the true state of the environment. And to do that, agents in reinforcement learning go away. They just have a function, and using that function, from the history, they produce their own belief states. And ideally, we will have the belief states equal to the environment state. Or, we ideally want it to encode all the information. Because the environment state could be like a multi-dimensional vector or a matrix, and has way too information that we even need also. Okay, so what's the major components of RL? We have policy, we have a value function, and an agent. So policy is what strategy do we choose for our actions. So given what state we are in, we choose what is the optimal action to get us to our goal. Value function is what we determine how good is this state that we're in. So like I said, like a final exam is not good. A birthday party would be good. And then a model. A model is basically how do we transition from one state to another. Say if we take an action in some given state, where will the next state be? And this is usually represented inside of the agent, if we want, and also the environment has its own model too. So in detail of policy, we have our state, policy, and action. It's just we pass it through a function and we get an action out. And the main goal in reinforcement learning is to learn what the policy is, right? And we can have two kinds of policies, a deterministic policy and a stochastic policy. And by their name, deterministic is just we produce one single action all the time, and a stochastic policy is you output a probability distribution and then you sample from that probability distribution to take a certain action. All right, and then we have the value function. We just input a state and then determine how good or bad that is, and we produce an expected reward. So as we said, a reward also measures how good or bad a state is. And this can be the expected return as well. So we have expectation here just to give us one value as a prediction. And then we have all the reward states. So we could get from some vector of rewards, we could get this one or that one or that one, and we basically just average them out, and some discount the future rewards as well. Right? And then for action value function, it's the same thing as the one above, but instead we have two inputs, the action and the state, and we get a value as the same thing. So, and then we have a model. So the model, instead, we want to see how we transition from one state to another. So we have a state, we input it into the model, and then we get the next state. That would be a state model. And then we have another one, a reward function, that gives us, inputs a state, and then tells us what was the most likely reward. And these two things are usually in, or by definition, are in the environment, because the environment knows what will happen next. And then based on that, we can give it to the agent, give the next state to the agent, we can give the next reward to the agent. But also, it would be beneficial if we could model these things within the agent, so then the agent can plan itself, like what, it could simulate basically what trajectories to go in order to maximize its reward. So here's the full picture for full observability. So basically, we have our agent and our environment, and we'll start here. We give our agent some state, and then we have the agent say, well, if we're in this state, then we'll produce this action, and then we give it back to the environment, and we just, now based on this state, or this action and the previous state, we produce the next state using the state function, and then we produce the next reward giving the reward function. And once we do that, we can take those states and reward and add it to our history. And then once we have that history, we can say, we can use that to train our policy based on that. So we know generally what states are good, what states are bad, and so that's how the agent learns. And then instead for partial observability, instead our policy doesn't act just from states, it acts from a belief state, which is a function of history, right? Because we don't know information of all the necessary information about the world yet. We first have to infer from our history. And each time the agent acts on the environment, we produce a new observation, a new reward, we append that to the history, and then the agent has to make sense of that again. And so we have this loop, and here are where all of the variables fit in. So, any questions so far? All right. Darcy? Yeah. So now we're gonna formalize everything in some equations here.
So, so an important part of reinforcement learning is the Markov decision process. And this is basically the process describing where if you want to move into a next state, it depends only on the immediately previous state and not the ones before that. So you can express this as the probability of having the next state given the current state is the same as the probability of having the next state given all previous states. So you can sort of compress your entire history into just knowing the previous state. And so this makes it sort of convenient to represent state transitions, which is moving from one state to the next, as just the current state action, the reward you get, and then the next state, which is S prime. So we talked a little bit about value functions. So there are two types of value functions. One is the state value function. As we said, it just takes in the state S and then outputs, given the policy, what it thinks the value of that function is. So we can call this as the expectation given our current policy of GT, and this is the return. So remember that's the sum of our discounted rewards. And that's the expectation of the return given that the state is currently S. So we also have the action value function. So now this, instead of just taking an S, it also takes an A. So we have the action function given policy, and given S and A, it's the expectation of future return. So we have these, we also define these useful equations called the Bellman equations, and their general purpose is to express value as a function of future value. And this just overall in the training process just sort of helps us hone our policy. So when you have, so when you're like in the process of training an agent, you're going to be like updating your policy. It might not be consistent, it might be bad. So we basically use these Bellman equations to update the policy function and just make it better and to get a higher return. So we have a different version for the action value and state value equations. And so sort of the overall purpose is to just express the current expected return as a function of future expected return. So as you're like looking at the next slide, just keep that in mind. We want to express current as a function of what we think is going to happen in the future. So for the to derive the state value Bellman equation, please don't get lost in the math here. But basically, we start with our value function given our policy and a state. It's the expectation of. So remember, this term is our return, and given the state. And so we expand this into the return for the immediately following time step plus discounted for all following time steps. And here we just expand the expectation, which is just a probability over the action in the state. This is the expected reward for the immediately following time step, and then this is the discounted expected reward after that. Oh, sorry. And so we can just formulate this as this nice equation here, where these first two terms, that's just the expectation. But then importantly, we have it in terms of the next immediate expected return, and then the discounted value function for the next state. So like this is the important part of this equation. We're formulating the value function of the current state as a function, of the value function of the next state as well. And so we can do something similar for the action value function, where we start with the action value function given S and A is the expectation. Remember, this term is the return given S and A. And now we expand that, so the immediate next reward and discounted future rewards. Okay. And then we expand the expectation. This is the expected reward. We expand this into the discounted sum of expected future returns. And then once we fully expand the expectation, we end up with this term, again, these few terms, which is essentially the expectation. And then the immediately following reward plus the discounted action value function of the next state and action. So again, this is the important part. We are expressing this value, the action value function of current state and action, in terms of the immediately following reward and the discounted action value function of the next state and next action. So
why this is important is because once we do this equation, all we have to do is just learn this function. And once we have that function, we can also just recurse a bunch of states. So that way, once you have the formulation, nothing goes wrong.
yeah, you don't have to fully look over this, just understand the purpose.
Yeah.
Yep, so. Wait, was Curtis doing this?
Yeah.
I'm sorry.
All right, so now we're gonna move on to deep RL algorithms. So the exciting thing about RL, even though it existed for say like 50 years or so, it's only now starting to get more popular because we have these general function learning things called neural networks. And neural networks learn those functions for us and based on our data. So, all right, so there's a lot of different algorithms that exist. And we can divide them into different categories. So first we have model-free and model-based RL. So model-free basically means we don't need the agent to internally know like what would happen next in order to function. So it's like basic intuition, or like a mouse or a rat just reacting to the environment based on like instinct. So it's like you say, I generally see this pattern happening, like there's generally good things in that direction, so I'll go that way. That's basically what model-free learning is. And you can split that into policy optimization and Q-learning. Policy optimization is basically you start with a random policy, so you do random things at random states, and then you slowly iterate that policy so that next time you know that it's going in the left is better than going in the right, and you weight that higher than going to the right or something. And then Q-learning, basically you keep track of these values, so you know the value function, you know the action value function, and you use that to determine what actions are good or bad. And basically, I'll go over that again. And then we have our model-based RL. Basically, we keep some model in our head, and we know like what would happen next given this current state, and we can plan things in the future. So we have these trees basically, and we have trees of states. So basically, based on those trees of states, we can estimate what path would be the best one through those trees. Okay, and some examples are like AlphaZero, and we can either learn the model or we're given a model. I would suggest going in this approach, learning the model, because it's often very time-consuming to design a model, and that's what my research is focused on, is learning models. All right, so we'll talk about these two. So Q-learning in a nutshell is basically you're given a state and you try to pick what action is the best at what state. So you can see our goal state would be S3 because it has the highest reward. And if we start at S2, we can see that the action towards S3 is A2, and then for S1 it's A3. And how does the agent learn the values for those actions is that it experiences through trial and error. And for policy optimization, instead we have a parameter space. So this is just like the parameters for our policy. And basically these are like the weights of a neural network. And so instead we start out at a random policy, and then we can just do like gradient descent, or gradient ascent in this case, because we want to have the policy with the maximum value. And we just do train based off our data. So to recap, the reasons why we have these two different approaches and why one would be better over the other is generally Q-learning learns the action value function, which is useful in some cases, and indirectly inferences the policy. So basically the policy is to pick actions with the highest value. It doesn't necessarily learn the policy itself. Whereas policy learns directly because that it tells you at each step where to go based on the state. And then Q-learning is usually more sample efficient, but it's hard to get working without a lot of tricks. And then policy optimization is more robust, but needs more samples. More samples, I mean like it takes orders of millions, in some cases, to train, and that's not good. So there's an approach called autocritic that attempts to combine the two. And also note that if you do model-based reinforcement learning instead, it is much more sample efficient because you simulate the world in your head and then you can plan based on that without having to actually experience the state before you know, oh, this is actually a bad state. Okay, so Q-learning.
All right, so as stated before, Q-learning is basically a reinforcement learning method in which we're trying to basically predict like a value function which is going to predict the maximum reward we'll get given some state and action pair. So it is a model-free based reinforcement learning method. And we're going to, it's an iterative process, so we're going to be receiving a lot of different states and actions, redoing multiple episodes, etc., etc. It takes a while to train, but once it it's kind of intuitive to understand, hopefully. So let's jump into it. So for this example, we're going to have an example environment. So here we just have a robot, and he's in a maze. So the robot simply needs to get to this end square right here. There are a couple rules to this environment. One, every time the robot makes a step in any direction, he's going to lose 1 point. That's simply to penalize him, saying, hey, we want to get here as fast as possible. Another rule is if he lands on a bomb, he blows up, loses 100 points, and the episode ends. If he lands on a power-up, he gets 10 points. And if he reaches the finish line, he gets 100. So there's only going to be 50 time steps, so it is going to terminate eventually. That's to stop the robot from indefinitely just going left and right, left, right, left, right. So a typical Q-learning cycle, we're going to start by initializing a Q table. Q table synonymous with Q function. It's just going to be essentially a 2D matrix, which is going to store all of our like Bellman equation stuff, and that'll make more sense in a second. Afterwards, we're going to choose an action based on what our Q table tells us it will give us the highest reward. We're going to perform that action. We're going to receive some reward from the environment. And after we receive that reward, we're going to update the table accordingly. Okay, so this 2D matrix right here is our Q function, Q table, Bellman equation matrix, whatever you want to call it. So right now this is initialized with all zeros because we have not explored this environment at all. So anytime we make a step, let's say so the starting point, let's say start is here, right? The rows are going to represent different states that you can be in, whereas columns are different actions. So that just helps you index into this matrix more or less. So if we're right here, we would have like the first row, and then there's 4 different actions we can choose. Each of these columns are called Q values, and it's going to be basically a representation of your cumulative reward you will receive towards the end of the episode, assuming you pick all optimal choices henceforth. So to start, once again, each one of these Q values is just going to represent this. So you give this matrix a state, a row, column. It's going to give you cumulative reward. I have to define one more thing, our policy. Who here remembers what a policy means? All right, so policy, basically you take in a state and then you're going to output an action. So in our case, it's going to take in this row. It's going to find whichever one has the highest value. Right now, they're all the zeros. We can imagine one might be 50, another one might be -1. It's going to choose 50 because it's the highest reward. And then we're going to choose that action. So if 50 was here, the action would be down. So once again, our policy at the moment is simply going to be, okay, given some row, we're going to choose whichever one of these columns has the highest reward, because we assume that if you maximize the reward, you're probably doing the best that the agent would want to be doing. In the case of tiebreakers, we're going to choose at random just to add some randomness and help it explore a little better. And later on, we're going to explain like what exploration stuff is. So just an update rule. To update, you might recall this is our Bellman equation. So essentially, let's say we start here and we go right. We lose like 100 points because there's a bomb. So given the state of start and the action moving to the right, our reward at this immediate step is 0 because we have not done anything yet. The reward we get for performing that action is going to be -100. We have a learning rate, which you guys recall from previous workshops. Discount factor, I'll talk about that a little more in a second. This expression is simply stating, okay, so after being in the next state, what is the most optimal thing we can do while in that state? So we're on the bomb, we already lost 100 points, but let's say the episode continues. The most optimal state, if on the bomb, if there was like a power up here, would probably be pick up power up. So in which case we would then, in the next state being we land on the bomb, the action we want to choose is go to the right, because that'd be picking up the power up. And we're going to end by just subtracting 0, which was the reward we had gotten from that step. Once again, discount factor is just a number between 0 and 1, and we basically use this to weigh how valuable are more recent actions as opposed to later rewards. So here's just a numerical example. Once again, let's say we start at this state. So the table is initialized to 0, which is why we have 0 here, here, and here. As you can see, the equation's right up here. So if we go right, this is going to be 0 plus learning rate 0.01. Negative 100 is the reward that we got. We lost points. Discount rate, we're just going to have 1 because this is going to terminate very fast. It's initialized to 0, so we don't know what the future actions would be. Mine is 0. So this is just going to equate to negative 1, because negative 100 times 0.01 is negative 1. Similarly, let's assume the policy tells us, all right, we're going to go left instead, because everything's initialized to 0, so choose a different random thing. Left is going to give us with negative 0.01. So you can see in the future, our agent is going to choose to go left instead of right from henceforth, because we have more reward here. Just another thing to state, so you might notice here we have 5 rows. It might be a more descriptive Q table if we instead had like 30 rows. So each state, instead of just being, we only have 5 states, it might refer to the actual tile that we're on. So this is a 6 by 5, I believe. So 6 times 5, 30 states. That would probably take longer to train, but would probably be like better overall. So right at this moment of time, we will likely come to a problem of, well, what happens if the optimal state tells us to go left, and then we get some points of just going right again, and then it just keeps going left and right? Because our policy at the moment is deterministic. That simply means it's always going to choose the highest value reward. So you can just get stuck in a cycle of like, it just goes left to right, left to right. So to break that, we're going to add in some probability into this to make our policy more stochastic. So in reinforcement learning, we have a general problem of exploration versus exploitation, or, well, this refers mostly to Q-learning. So exploration is basically adding randomness to our decisions in order to like find more optimal patterns we probably wouldn't have received if we did the optimal thing from this time step, if that makes sense. Whereas exploitation is taking advantage of our existing data, and then just like with our Q table, it would be the sense of, okay, the most optimal thing for us to do is move to the left. So it's just going to pick the highest reward every single time, and that's going to be a very deterministic thing. So we want randomness, just to say that one more time, because randomness can help us explore different paths that we wouldn't otherwise. So you can imagine if the rules were different and maybe we had to encounter a bomb first in order to get like 1,000 points from some other tool. The second it encounters a bomb without exploration of doing randomness, it's never going to go in that direction again because it lost points. So to implement this explorative mechanism, in Q-learning we use a greedy strategy called epsilon greedy. And basically all this says is we're going to define some probability of doing a random action. So let's define epsilon equal to 0.1. This just means 10% of the time while training, we're just going to pick a random action regardless of what the policy says. So this randomness will help you kind of just stumble around and eventually find a very, very good path into whatever you want to do. You can do more stuff with this epsilon. For example, some people will often have the epsilon like decrease over time, over iterations. So you can have a decreasing epsilon. You can have it exponentially decreasing, however you want to treat it. But in general, having randomness for training is good. And then once you want to like test it, you'll generally turn this epsilon to 0, and then you're only going to use like the explorative way of pursuing stuff. So, anyone have any questions thus far? We good? Yes? No? Puzzled? Okay. So if I were to ask you, all right, instead of a maze in which the states might be represented as 1, 2, 3 as integers, we now have an image. An image can be RGB, 3-dimensional, lots of different pixels. That doesn't really make sense how to plot that onto a 2D matrix. If you guys can think of a way of doing that, by all means, but it's probably going to require an enormous amount of RAM. So instead, in Q-learning, we include deep neural networks in order to kind of solve this problem. So you can imagine, instead of having our 2D matrix, we'll instead have like a convolutional neural network, and the output of that network is simply going to be our Q values. So we're going to train a network in order to actually predict each of these Q values in this table, as opposed to like trying to map like who knows several 100,000 values into a matrix, which that would take forever to learn. So deep learning can be used if you're doing like game stuff, and yeah, it's also better when you have continuous like state spaces. So this is just a diagram to show how this would kind of look like. Q-learning, you would give it the state, so it's no longer you're giving like the network a state and an action. Now you're kind of just giving it a state. It's going to give you what it expects various rewards will be for all the actions it's allowed to take, and then you as the user can then choose, okay, which action do I want to choose at this step. The only tricky part of this is how do we train this now? So our predicted, once again, will just be like, let's say we take the maximum Q value that this outputs, that'll be our predicted. And the actual, well, what does actual mean in this context? It's not like we exactly know what is the most optimal thing to do if I'm playing like Dota, League of Legends, or StarCraft at this moment in time. So we kind of like predict the actual as time goes on. So what we tend to do is we'll say, all right, actual is going to equal whatever, we're going to include the Bellman equation back into this problem. So our reward plus discount of the maximum future reward we will have. So once again, this expression right here just means, all right, we already did an action, we're in some state, we got some reward. Okay, so now that we're in a new state, what is the maximum reward we'd get if we were being like optimal, which shows the best action? So that's what this means. It's going to be the reward of the next step. And we would basically treat this as our actual, then do, for example, just sum of squared means loss. One thing you might notice is this might not necessarily be like the best label because we're still using our model to give it a label. But even though that is not an entirely correct label per se, there is some truth to it because it does have the actual reward you got at that step. So while this does take a while to converge, it will eventually converge. So deep Q-learning tends to take a while to actually train. Some notes on that. Once again, deep Q-learning takes a while to train. We have to do 2 forward passes because we first have to predict like an actual reward, and then we have to predict the future reward, which implies 2 forward passes. We're doing gradient descent in between time steps, because each of these cumulative reward things are a actual time step. So doing gradient descent on that, gradient descent with a discount rate, with a learning rate, is going to be very slow. But in general, will require less memory than like vanilla Q-learning, because as recalled before, how do you map an image onto a matrix? Doesn't really make logical sense. So one I guess intuitive difference of how I tend to distinguish between policy gradients and Q-learning, policy, which you're going to learn right now. For Q-learning, you're essentially just predicting, okay, how many points am I going to get if I do this action? Whereas policy gradients is predicting more so, okay, which action should I be doing right now? So you can imagine kind of just like a very high level idea of what that means.
All right. So we'll talk about policy optimization. So first, to do that, we have to define our data set. And we'll just say our data set equals a bunch of trajectories. Well, what a trajectory is a bunch of tuples, state, action, rewards, at each time step. And we consider one trajectory to say how long, agent in Super Mario goes until it dies. That's one trajectory. So now we're going to revisit the policy. So if we have our stochastic policy, we have given our state and some parameters, we produce an action. And so this is a probability distribution. And we also define our performance function. We're just going to label how good this is based on what our expected return is. And we can estimate this basically by let our agent run in the environment for several simulations and then just count how much reward it got during that time and get the average. And then you find out that's how much it scored for its performance function. Okay, so it's similar to a cost function because cost function is instead the inverse. Like you don't want a cost function to be high, but you want the performance function to be high instead. All right, so to learn a better policy, we want to find how to change our parameters in such a way that we increase the performance function. So, and to do this, we do use gradient descent, or the negative, or gradient ascent. So basically, we could take the negative of our cost function and then, or our parameter performance function, and treat it as a cost function for deep learning. So if we did that in our code, it would look like that. And we just use the traditional gradient ascent update. So it's ascent because it's plus instead of minus. And we take the gradient with respect to our policies there. And here's what it looks like. We start in some parameter space at some point. We say what is the slope in what direction to increase the policy, and we just take one step in that direction. So to do that, we just pass it into this function, this equation here, and as I said before, we have our parameters at the next step equals the parameters at the given current step plus some small learning rate and the direction of increase. So this is the gradient, and we just take that with respect to the parameters of the policy of the performance function of the policy function. All right. So how do we actually calculate this gradient? Well, to do that, we have to derive some formula. How much time do we have? I guess we'll go through that now. So first we start off with the definition of the performance function, which is the expected return over the trajectories sampled by the current policy. So we just try to estimate what this policy currently values at. And so to update it, we need to find what is the derivative of that. And so here's the math. So we start out with the derivative, and that equals the gradient of the expected value. And we expand what does an expected value over rewards mean, and that's just the probability of getting this reward or this trajectory and times the probability or times the reward of this trajectory. And we take the integral over that because that's the definition of expectation. And we go from here to here. So now we just move the gradient sign inside of the integral. Just because of calculus rules, you can do that. And then from here, we take the probability and we just take it and we multiply it by the probability of the trajectory over the probability of trajectory. And so that would be 1, so this cancels out to this. But now we can say this instead looks like the derivative of a log of the probability. And so now we have this equation. And once we have that, we can turn this integral of probabilities back into an expectation form. And now we complete it by saying well, we have it in terms of trajectories, why not we put it in terms of states and actions? So all this complicated math is really just expanding out what is the probability of a trajectory. Well, probability of one single trajectory is you have to consider the probability of each individual state at all the future time steps. So it's basically a recursion of states. So you consider the probability of a certain state given the previous state in action, and you say what is the likelihood of taking this certain action given our policy, and we recurse to the next state. Like, what is the probability of this next state given that we take this action? And so based on the chain rule of probability, we can find the probability for the whole thing. All right, so what we're doing here instead now is we're just saying, what if we take the log of the probability and then this turns into a sum instead? And then what if we take the gradient of the probability and we say that's equal to this equation? And then we turn basically a gradient into our new equation here in terms of the policy. Okay, so after we have that, we can say go from here to here, and yeah, this is what we did before. We just took it and expanded it into our states and actions, and we include our policy now. So now that we have our policy, we can do backpropagation because we have a clear path going from state all the way to reward. And then once we get the reward, we can do backpropagation through every single parameter, and then we know what the weights are. Okay? So this is the final policy gradient. And basically we use this, we want to gather our data, so instead we collect an estimate of this thing here. So we take an estimate of the gradient because we're doing gradient ascent, and we just use this formula to calculate what is that estimate, and we use that estimate to compute backpropagation. And then basically, as you can see, instead of doing the gradient of the performance function right here, we take the estimate and put it there instead. And so we always update this new estimate based on the policy, because as the policy parameters change, we have a different evaluation for the performance function. So we have to keep doing gradient descent and keep getting new estimates of our value, so then we can eventually converge at the right one. So this is the algorithm for vanilla policy gradient descent. So the only key difference that I didn't explain here was the advantage estimates here. And basically what this is doing is just complicated math for deep learning. It's just doing gradient descent. So advantage estimates, basically, in the short time I have to explain it, is how different is this action from usual. So it's basically what it is the value function, but you have the value function for an action subtracted by some amount, because that's like the usual value. Say at each time step you get a reward of 1 because you didn't die. Then you would subtract 1 from that value because it's not anything unusual. Like, you want to see what is actually usual, and so you subtract that value to see, and so the agent learns what is unusual and takes those actions that are more meaningful. Okay, so I have an implementation. We also have an implementation on Q-learning, but we'll post that up in Piazza if you want to look over it in more detail. I just wanted to end on some expectations versus reality. There's a lot of problems in deep reinforcement learning, actually, that you need to hurdle in order to do something novel. So here's a good article. Like, it tells you a lot of problems. So like it can be sample inefficient. Like you can see like there's millions of frames that's involved, sometimes billions, and like there might be behavior that you don't necessarily want. For example, here's an example of just like the ship has just learned to spin in circles because it finds out that it can exploit the game to produce a lot of reward. And so it just does that because that's the highest reward it can get, basically. And then there's like other examples, but there's a lot of problems with reinforcement learning, and that's why it's an active research problem. And it's not necessarily used in industry because of those problems. So you can find like local optima, it flips over and starts running. Here's one. It is fun to look at these, but yeah, it just does some weird stuff when you do it in practice. And so converging on like the global optima is pretty hard. And you can see like not even just like with random setting the random seed can result in the wrong behavior. So that's really crazy, because if you just start out randomly in a different policy, it doesn't necessarily converge to the correct policy. And so like 70% failure rate is pretty huge. And like here's like a diagram for why machine learning is hard. It's just like there's so many things that can go wrong, basically. Yeah. So to end here, there's a lot of research directions, because obviously we haven't solved AGI yet. But the reason why RL is a good way to AGI is because it's so general in a framework that you just put something in some environment. Like you could put a robot in an environment and it'll figure the environment out. So that's why it's a good model for our robotics and research. But there's still these problems. You can read them on your own, but I do this one. I want to do that. There's a lot of things I want to do, to be honest, but to end, here's some good resources if you want to study this more. Recommend the official reinforcement learning textbook. I read through it, it's pretty good. And then there's Spitting Up and DeepRL. If you want to just skip to the meat of it, it has all the state-of-the-art papers and gathers all the resources necessary. It's by OpenAI, if you like their credibility. But yeah, that's it.